This lecture will cover the basics of color Doppler and pulse Doppler artifacts. So color Doppler and pulse Doppler also have their own artifacts. They vary a little bit from all of the 2D black and white artifacts that we've just covered, and that a lot of these can be corrected by the user. Also, we haven't covered color Doppler or pulse Doppler very much in physics as of yet. So these are very basic explanations of what these artifacts are, as they do fit in with this chapter, but we will most likely cover them again when we get into the color and Doppler chapters as well. So make sure that you have a basic understanding of these four artifacts, being mirror imaging or crosstalk, aliasing, ghosting or clutter, and twinkle artifact. So again, as I just said, color and pulse wave Doppler artifacts tend to be a little bit more on the user error side of things, or interference from talking or other outside forces. So there's not so much going to be a violation assumption as an error in how we're operating our machine. Again, typically we can correct these errors using machine parameters, and some of these errors that occur are helpful in recognizing pathology. Twinkle artifact helps us to point out kidney stones in the kidneys. Aliasing helps us to find the fastest moving area of blood so we can get accurate velocity measurements. So again, sometimes these errors are actually helpful. We just need to know how to use them and correct them appropriately. So we talked about mirror artifact in the propagation artifact lecture, and it actually also pops up in our color and pulse wave lecture. So similar to grayscale, the color Doppler can be displayed across a strong reflector. We see that quite commonly with the subclavian arteries. The posterior wall of the subclavian artery acts as that strong reflector into which the same reflector is reflected across, and we get that mirror image. So typically the mirror image is going to be deeper and less intense than the true anatomy. We also see mirror imaging or crosstalking in when we turn on our pulse wave Doppler. So this is going to be showing the same waveform on either side of the baseline. Typically our true waveform is going to be brighter, where that crosstalk is going to be at a decreased gain. If we see that crosstalk, we can change our gain settings. We can turn the gain down to get rid of that secondary waveform, or we need to change the angle as to which we're coming in at how the blood is flowing. If we come too close to 90 degrees, we might catch it flowing in two directions. So we want to change that back to at least a 60-degree angle. So again, to correct mirror imaging and crosstalk, we're going to change the angle that we're coming at the vessels or area that we're Dopplering, and we can try to decrease our gain as well. Aliasing is a concept that in using color Doppler and in pulse wave Doppler, we have what we call a speed limit. It's also called the Nyquist frequency or the Nyquist limit. So if our velocities are going over what we tell the machine is our speed limit, then what's going to happen is it's going to wrap around and register as a different speed below the baseline. So over here on the side, we have our color map. We're telling the machine that this velocity is our speed limit. If a velocity is traveling faster than this, then it's going to wrap around and start to be displayed as one of these negative velocities below it. Aliasing is helpful in determining where really fast flows of blood are. For carotid imaging and for a lot of vascular imaging, we want to find that fastest little bit of flow because that is the true velocity through that area. So we can see in our picture here, this area right here is being displayed as that light green into the blues. This isn't a negative blood flow, but rather an area of aliasing that is exhibiting very fast blood flow through this area. So in this case, aliasing in color is actually helpful in letting us find that very fast jet of flow. It also happens when we are turning on our pulse wave Doppler. If we were to put a gate in there and Doppler the area, again, our speed limit or our Nyquist limit is at the very top of our spectral window. If the blood is moving faster than what we have that set at, it's going to come up and wrap back around. We can almost take this section here and plop each of these on top of our waveform, but because our graph is not set high enough for that, it wraps back around. So to correct for aliasing, we're going to increase our scale, also known as PRF. We can try changing our baseline, so we can take this line here and drop it down into our spectral window. Or the last thing that we can do to correct aliasing is just get closer to the area that we're imaging. Also has to do with the PRF. Again, we'll learn more about aliasing in depth in the pulse wave chapter, but just understand that aliasing is going past that Nyquist frequency or Nyquist limit. The formula for the Nyquist limit is PRF divided by 2. You will also want to memorize that. So ghosting and cluttering then is color or waveform information that is being displayed when it's not true movement or true color that should be displayed. So over in our example on the side here, we have the color gain set at 44% in the first picture, and we're not even showing flow in most of that vessel. In the next picture over, we have color gain set at 65%. We're getting appropriate flow through this vessel, and we're actually catching appropriate flow in all the other little vessels around it. If we were to turn our color gain all the way up, yes, we get flow in the vessels that we did previously, but now we have all this other junk all around it. So that's that kind of cluttering or that ghosting that is out in the tissue. It is just the machine being extra sensitive to little vibrations out there. It's not true movement through a vessel. And same thing can happen if we set our spectral wall filter incorrectly. If we set our wall filter at 50 Hertz, we're telling the machine to display any reflections that are coming back at 50 Hertz or greater, and so we might get these little junky things within our waveform. If we were to turn our wall filter up when we're now telling the machine to display anything at 75 Hertz or greater, you can see that there's actually a gap between the baseline and where our waveform starts. Gets rid of all that little extra junk stuff, but are we getting rid of too much? You never know. If we were to turn our wall filter up super high here, we have it at 550 Hertz, we're saying only display anything that's higher than that. We've got this huge gap from our baseline up to where our waveform starts. We've really changed how that waveform looks. So not only can we falsely represent our waveforms by turning the wall filter up too much, we can falsely represent them by having them too low, and we're getting that extra noise or that ghosting and cluttering within our spectral waveforms. So how do we correct it? We're going to want to increase our PRF, increase the wall filter, or decrease the gain. The last artifact that uses color is kind of an interesting one, and it actually helps to detect kidney stones and gallbladder stones, that kind of stuff. So it's called the twinkle artifact, and we see it typically behind really strong reflectors, those being calcifications or biliary crystals. Using color to detect these strong reflectors can actually be more sensitive than looking for shadowing that we would expect to see behind them. And the twinkle is caused because there's just extra noise coming up from behind the reflector. Typically these are viewed well if we move the focal zone above the area that we want to see that twinkle at, and then turn our color down to a moderately low PRF. So here we have the bladder, and we have a stone right here, and we're seeing all this information behind it. This is all twinkle artifact coming out from behind that strong reflector. If we were to put a pulse wave Doppler in there, all we'd get is all this crunchy little noise over here. It'd sound just gross, because it is just extra noise that's happening behind these strong reflectors. So if we are getting a twinkle artifact behind something that we're not trying to diagnose with that twinkle artifact, then we want to correct for it, and that'll be by increasing our PRF, so we're not as sensitive to that extra noise back there, and decreasing our color gain, so we're just not picking it up as much. So again, kind of a crash course into some color and pulse wave Doppler artifacts. These will pop up again later in a subsequent chapter, but for the time being, just know the 4 terms, know what they look like on ultrasound, and how to correct them. So number 1, if a vessel has a mirror artifact, which one is the real vessel and how can you tell? Number 2, aliasing is helpful to find the fastest flow through an area. What must be exceeded for aliasing to occur? Number 3, what artifact occurs when there is color outside of true movement? And number 4, once again, think of a question that you have about this lecture.